design and quick layout. And that's my quick layout. It's my favorite one. You know, it's the chart title, this and all this stuff. Yeah, also, I'll show this again real quick. Look at all these options. You got so many cool things. It's so nice.
Gary! I was just looking for the sports channel, Gary.
How's everyone doing? Good afternoon. Good to see you. Doing way better today. Thank you everyone for all the positivity last week. How many people do we have watching? I'm a little bit scared right now. Who all do we have watching right here? Say hey if you're here in the chat. It says 15. What? 15 people watching. You know what I'm doing? Brian goes a little crazy when there's not. What's going on? Where is everybody? No, Nathan, good to see you here. William, good to see you here. Clayton, good to see you here. Throwing 1,000 points in the chat. Just going a little crazy right there. Doing much better. So last week was really rough. And thank you everyone for bearing with me last week. Last week I've probably said this a billion times now. On Saturday night, I got like no sleep. Sunday night, I got like 2-3 hours of sleep. Monday, you're just starting. Just starting the exam. So I wasn't getting much sleep last week at the start of the week, and I was in pain. So that was really hard to like get everything because of the exam. Maybe people think we don't have class because, well, the exam. You're talking about the. Well, why wouldn't we have class? We'll start talking about the exam right here, but no, I'm doing way better this week, and last week was just. Everything was thrown for a loop last week. It was very hard to kind of get everything on track with just everything. But doing much better this week. Way better on track. Now the shirt is not green screening. I don't understand life sometimes. But how's everyone doing? Megan, Lindsay, Nathan, Veda, good to see you here. Walker, good to see you. Wilton, good to see you here. Reed, good to see you here. Hunter, Emery, Clayton, good to see everybody here. But because of the upcoming exams, well, we have upcoming exams. Maybe it's because there's no big assignment due this week, but let's go take a look at the take-home, and let's start talking about that take-home. Here we go, talking about the take-home. So the take-home has been posted. There's obviously class ball, and good to see you here. Do not cheat on this. Do not cheat. We do have people who cheat, and it makes my life not fun dealing with this. Do not cheat on anything. Do not receive answers from people. Do not, people are like, hey, I've got these answers and such. Be like, I got to do my own work. I do want to say this also, is that it's a lot of what we do in these courses build. And one of my favorite examples is Kenny, who took 201, 320, 474, 475. And when he got to 475, Kenny is an exceptional student. He might have just finished the master's program. But as these built, you can't, no. Do not collaborate on this. Do not collaborate on this. This is all your own work. This is all your own work. This is all your work must be your own. Do not collaborate. Kevin, thank you for asking. Do not collaborate. Good. Kevin, you crack me up. You kill me, man. Only question, but what the heck is speed grader? Oh, that's how we can view things. Yeah, that's how we view it through here. We view things through speed grader. Thank you for asking about that, Max. Yep, that's how we view things. I view, like when you submit stuff, we view it through speed grader. It's not, you might as well call it grader. It's just a normal grader type thing. And then we go and grade it. I'd show you it, but I'd be showing student work. If someone super wanted, they'd have to be like, you can show my, I don't know. I'm too afraid someone's gonna be like, he showed my work and I didn't want him to. It's just how you grade things. So with this right here, someone's already submitted. Whoa, great job, whoever submitted. With this right here, this is an R data file. Can anyone explain to me what an R data file is? What is an R data file? What is an R data file? Like what will an R data file give you? What will an R data file give you? Who knows what an R dat file is? What is an R dat file? What is an R dat file? What does it give you? An R data file is a what, and what does it give you? Important we know what an R data file is. I'll give you a hint. What's an R data file give you? Who knows, for 50 points in the chat, you should know what an R data file is. It's like a what for R. There's a lot of words you can use for it. It's not a script. Good guess right there, Max. Good guess. It's not a script. Not really instructions. Alyssa, good guess also. Let's throw some more points out there. Some more points. Not a data frame. Not a data frame. So this is why I'm pausing on this and asking the big question right here. An R data file is an environment or a brain. So you can go right here to load. This saves an R data file, saves your workspace. It's a workspace, but it's like all the things you learn. Now, if you open this, yours might not be set up. I would suggest going here. I got to blink my screen and click the button and then open what you just downloaded via this method right here. And what you should see, there it goes, is you should see this loaded in. This is how to do it. Now, because I have these associated with R, mine are associated. Yours might open in R, not in RStudio, it might open in R. But you notice mine asks if I want to load this, and it loads it in right there. So this is the code it's running. I've also re-downloaded it on my computer now. It's fall. Oh my gosh. It's fall. I literally named this file last night. I call it spring. I call it... I don't know what semester it is. So right here with the function, did I go through? Do not do what Brian's about to do. Did I call it that? Don't do this. Do not do this. I did call it fall right here. Cool. Okay, don't do that. This is what you don't want to do. This is the review quiz grade muted. It looks like it is muted. I'll unmute it here in a moment. Let me unmute that Emory so you can see it. You should be able to see it. So we'll do that after this right here. We'll talk about that too. So with this right here is the function. And you may not know, but you can actually see functions if you run this. This is not what you want to do. A lot of people also do the following, which is viewing inside of it. This is not what you want to do. Now, there are things here that are required that you don't actually need. I'm probably going to go in and update this later today and remove out these require right here. You do need reg class. If you don't have these other packages, what would you do? What would you do right here if you don't have these other packages? Who knows? A few people have already done this. What would you do right here if these other things are not going to load? What would you do if you don't have a rules, if you don't have caret, if you don't have proc, which is for ROC, RO stuff right there? What would you do? Install packages. So it's important to know how to handle these. I almost think it's a decent, like, do you know what you're doing? You would install the arules package if you don't have it. So make sure to install those packages if you don't have them, if it's already crashing for you or something like that. You don't want to be viewing the function. That is not the goal right here. The function is going to take your what as an input. The function is going to take your what as an input. The function is going to take your one. Great job, everyone. Will and everyone following along. The function is going to take your what as an input. I feel sometimes people skip these portions, but this is like super important. If you don't know how to make the student ID right here, Megan, amazing answers. It's going to take, and we go make.exam, and we enter in our student ID, which is 000000. That's our ID. Now, what it did is it made an exam for 0. This will not be yours. This was an RMD created for you. And so we're going to go and load this RMD file by going to our computer. You can search really quickly on your computer, and you should find it. There it is right here, exam for 0. And we have loaded it up. So this is the file it created on your computer. You should get an RMD file created on your computer and 2 data frames. Now, a lot of people have asked, can I work on this in parts? If you want to work on it in parts, what do you think you should do to this environment? Here's the thing I would do. If you want to work on this in parts, what do you think you should do to your RMD, and what should you do to your environment, which is your workspace? You should save it. So you can go right here and save your workspace and call this like exam or take home workspace. So if you want to work on it in parts, you can do it in parts. So save this right here. Save, like this will save this. And what kind of format will it save it in? If I save this right here, what format will it save this thing in? There's a review now of this thing up here is a what type of file. 50-point question. That thing up there is a what type of file? So when you save a workspace, you could, doesn't hurt, just lets you see the only things up there. It won't hurt anything to not clear it. Close, Megan, super close. Not a r.dat, but a .rdat. You can see right here in the codes we were in previously, it's an r.dat file, an r data file. So an R data file, exactly. Alyssa and Megan, great answers right there. More points out to everyone. It's an R data file, so R data. So just kind of seeing that right there, and that is what it's called. You could probably just do save. Like, I bet we could go right here, watch this. Save, and let's say work, midterm. Oh, I was trying to save. Yeah, I don't know. You just go here to save button. Click save button. Let's see what code it runs. And we're just going to call it work. And that's how you should write it. I don't usually write that code out. Save image. It's save image. So it's like kind of like saving a disk image or stuff like that. So now I've created this and we could load it back. Like if you look right here with the load function right here, if we were to do the same thing, but we were to write it out, I don't love writing these things out. I like using the push buttons for these. If I go to work, but I clear this and then I load it, it loads it back in. Does that make sense what's going on right here? Like I saved this, so if I ever want to come back to it, I can do it. So now if I wanted to reload it, I saved it. You could, once again, just use the buttons. These buttons will save and store that stuff for you. Is this making sense to everybody what we got going on right here? We now have our data. We don't actually need the make exam function anymore, so you could technically remove that. Makes sense. That's what we like to see. I don't want anyone confused on this because somebody is going to be very confused the night before the exam. They're going to be like, what's going on? We don't want to run it as a function. We want to remove it. Really? There we go. Remove that. You don't have to do all this. Environment's nice and clean now. Let's look at the first question. You entered your student ID as 0. That's not going to be your student ID. So make sure to save this because I have had an issue where people mess up their student ID. You will be submitting what 2 things? When you look at this right here, what will you be submitting when you turn this in? What will you be submitting when you turn this in? I think this should go to the form. What will you be submitting? Let's go right there. What will you be submitting when you turn this in? What 2 things do you need to submit when you turn this in? You need to make sure you know this. This is where if you make this mistake, it's bad. We'll probably take off like half points if you don't submit both. Not the doc though, not the doc. Oh yeah, you're correct. Megan, you're right. You're saying the Google Doc, right? The Google Doc. Yeah. When I saw doc, I thought Word document. Do you need to knit it? Do you need to knit this? Do you need to knit this? This is a huge change for people. Do you need to knit this? Do you need to knit this? Yes or no? Yeah. No, you don't need to knit this. I don't even try to knit it. Don't worry about knitting it. If you try to knit it and it fails, just don't do that. Don't do that. Don't knit it. We're just getting a copy of your work because we've had people enter in things like the wrong ID and then it gets graded incorrectly. I've had students make like C's and D's because we can't grade their midterm. Because they'd be like, well, can you look over my work? And it's like, I can't even check it because I don't know where your answers come from because I don't have your questions. How'd you get data 1 and 2? How did we get data 1 and 2 in the global environment? How do we get data 1 and 2 in the global environment? What do we do to get the data and get our exam file right here? How do we get our data and so who can explain right here? How do we get the data and how do we get the exam file? How do we get the data? We run the make.exam function with our student ID. So that'll load it in. That'll run the make.exam with your student ID and that'll load it in. And then we've got it. I don't know why the shirt was green screening earlier. Now it's not. So good questions right there. Any other let's throw some more points out to the chat. Any other last questions? Great job, Walker, right there. Thank you, Walker. Excellent comments. It's because you cleared. Yeah. Re-go through the steps. If you have problems, you might need to delete your files, like delete the files and restart. Make sure it's working. Reach out to me. I did that, but I don't have data 1 and data 2. You should. You might have made your exam twice and it might have crashed because I think if we run this twice, it might actually get mad at us. Can't find function make exam. Let's bring back the make exam function. I'm going to load back the make exam. I need to load. I need to go way. Okay, here we go. When did I first load it? Okay, there it is. It might actually get mad. No. There we go. Try rerunning it. Tell me if you don't see it, Veda. We might have to take a look. But it should do it. If you couldn't, because I deleted the function again. Should do it. Tell me if there's issues. We might have to take a look. Just make sure the make exam file is right here. You see it's mad because I already have the file, but it's still creating the so overwriting. That's weird right there. Overwriting. How are we looking, everybody? Is it working? Please contact me if it's not working. You could run into issues very quickly if it's not working. Like later on. We'll go back to the main screen here, but please contact me if it's not working. Looks like a lot of people have it working, which is good, and there's a lot of time, so we'll get it working. Let's unmute those quiz scores so people can see how they're doing on the quiz. Let's unmute the quiz scores. Man, thank you so much. When people, I think it was this chat that put B in the chat for Brian, that meant a lot to me when I was not feeling well and I had to take a 5-minute break. I think I told people during office hours, I just literally laid down on the ground. I was just like, I'm going to lay down on the ground right next to here. I need 5 minutes of lay down time. Okay, let's unmute the grades. Post grades. I don't know why it's muting them. All right, it's posting the grades. You'll get to see how you did now. This has unlimited attempts. Great grade posting policy. Automatic. There we go. Okay. It should be posted automatically now. You can see how you did. You should be able to see what you got wrong. So we have some people who have attempted it. We're section 5. Let me go over here to us. I think it's a good like, where do you stand? So we have it posted now. And you can see how you did, and you can see your scores. So take a look. Your scores are now posted on it. It was the grading post policy. Oh, yeah. Lindsay right there. I'm just laid out on the ground right here. But I'm doing way better today. It was really like Monday, Tuesday last week was horrible. Wednesday, Thursday was bad. And then Friday, Saturday, Sunday. Like Saturday was the last day I took any medicine. So yay! And thank you again for all the well wishes, everybody. Well, the other thing we got to talk about here is the review quiz. So the review quiz is a good idea to see what the test is going to look like. Now, what also do we have right here for the review quiz? And maybe I'll do 2 questions on the review quiz. Let's talk about 2 questions right here. Let's go to the main thing. Okay. So what questions, take your pick. I'll do the first 2 questions people say. You get to pick one, but I'll explain conceptually what's going on with 2 questions. I'll explain conceptually 2 questions. I don't want to do the whole quiz, but let's do 2 questions. This is a good example of what the test will look like. Remember the test, you get a 1-page front back sheet. The test is next week. I don't want to missay the date. The test is, let me go grab the date for the test. Test is coming up here next week. There is no assignment due this week except for the upcoming midterm and the practice right here. The test is midterm placeholder. And is this 320? Good. Don't want to say the wrong date. The test is Wednesday next week. That's going to be awesome while I'm doing the 201 test. So once again, big test week this week. Question 2 people want, you bet. We'll do some question 2. And so this is a good example of what's on the test. But with this, what should you also know? The 27th, yep. I'm going to have a big 27th with 201 also. So one thing where people are going to lose points on the test is people will lose points on the test doing what types of questions? Where do you think I think people are going to lose a ton of points? Which is the easiest thing to put on your cheat sheet. And if you want a good cheat sheet right here, this has more than we've already done, but it also has what we've been doing in 320. So where do you think people lose points on the test? This is Brian's advice for where people lose points on the test all the time. And it's one of the best things to put on your cheat sheet, interpretations. We have not done this. So I was doing this today in office hours with 474, going through some examples. This will be indicator regression, which we have not done. But the top one right here is the interpretation for a quantitative X in multiple regression. So these are quantitative X's in multiple regression, which is where we've gotten to with our interpretations. So make sure you know this right here. 2 observations that are otherwise identical because we're doing a multiple regression, but different X by 1 unit are expected to differ in Y by BI units, B sub I units, where the observation with the higher X is expected to have a higher, lower Y. Make sure to have this down. Make sure to look at your homeworks. Make sure to practice and get it down and ace these interpretations. Big hint for the test right there, about the biggest possible hint I can get. So with this right here, we need to look at the correlation. This goes back to 2 quantitative variables and analyzing correlation. So there's only 2 choices right here. What are the only ways we do correlation right here? So if you see a question like this, you can narrow it down to 2 choices pretty quickly. What 2 choices would you... I'm going to do 3 questions right here, and then we'll hop to some lecture. What 2 choices would you narrow this down to? There's only 2 choices here that we should pick from. Only 2 choices we can pick from. Pearson and Spearman. So, because R squared is a value of percent of variation Y explained by the variation X, p-value is statistical significance. Correlation is either going to be Pearson if it's linear, or Spearman if it's got a monotonic relationship that monotonic means goes in one direction. So it could look like an S. That's why we talk about the S of the Spearman. And Pearson's going to be more linear. I see some key features, though. I see some sort of like this. What am I trying to point to you here? I'll draw on it. Let me draw on this right here. So let me draw some features for you I see of this. And I'll see if you see the features, too. One feature I see is this right here. What feature am I seeing right there? Heteroscedasticity. That's not good for one of the two. We might also have issues with something like these. One might be issues here. Yeah, perfect answer right there, Max. That's exactly what we want to see. So there's got outliers. Does a line go through the data? Maybe. I don't know. Maybe. I don't know. Maybe there's a little bit of a bend too. So this should scream one of the two to you. When you see this, like this one right here is a pretty obvious choice for one of the two. It's got heteroscedasticity, it's got outliers, it's got a some maybe nonlinearity to it. So that's going to be majorly one of the two. Like this is good. Like definitely we're going with this one on this one. Like it's got lots of features. Spearman, boom, Spearman. Pearson needs to be just a good linear relationship. Just think of your classic correlations. If you're wondering what does Pearson, that's a very strong Spearman right there. Pearson is just going to be like, that's what you want to see with Pearson. You don't want to see the unequal spread. You don't want to see the outliers. Spearman's the rank. Spearman is called rank correlation. Crazy data, get your Spearman. I love it, Megan. I think here you go, another 100 points. Megan's got those quotes right there. Yep. Oh, forget about our jokes. A lot of classes don't know we got some jokes. Excellent work right there. Me about speaking of those points. What other question do you want to talk about too? What other concepts or questions? And this is the good stuff to know. This is the practice, because if you know the answer to this, it's one thing. But what other question do you want to talk about? Pick two more, and let's do two more here. Number 5. Listen, number 5. Okay. What is your conclusion regarding the following graphic? Okay, so let's think about what we look at right here. Got a lot of output on the screen. And let's look at what we're comparing. I'm going to zoom in just a little bit here. There's really only one thing we need to look at here. Okay. So when you look at this right here, we're comparing males and females. We're comparing the minutes they talk on phone. So we're comparing males and females and the minutes they talk on the phone. Now, these are box plots right here. You can kind of see where the medians differences are. There's the difference in the medians, small differences. Then we have here the histograms. What are your thoughts on histograms? Which, yeah, you maybe could here. But what are your thoughts on histograms? What are your thoughts on histograms? Let me do number 8 after this. And we will do a Kahoot review for this class. I've got enough time to set it up. We'll probably do the Kahoot review on the weekend, maybe. We hate them. We don't like those histograms. But sneak a peek at those histograms. What do they look like? We don't like histograms, but maybe just take a little peek at that histogram. They look horrible, right? Boo histograms. So what do we want to look at? And the histograms are so bad that it's going to be So we want to look at the QQ plots for normality. QQ plots is where it's at. QQ plots are where we want to look. We want to look at the QQ plots. Histogram is Lane Kiffin. Yeah. We don't like those histograms. And what am I pointing to you? We want our QQ plots to follow the line. We don't want our QQ plots to bend away from the line. Megan's cracking me over there. So this right here is issues. Don't look at the histograms. They can trick you a lot of times. Those are actually so bad that the QQ plots are so bad too. Down here is where we generate our what's. At the very bottom of this, these are the permutation tests. And you could actually tell you, I could ask you, what is the p-value for all tests? Can anyone tell me the p-value for all tests? There's 3 tests right here. What are the p-values for each of these tests? You can actually discern it. But these are the permutation tests, perm test. So the p-value for all tests are actually 0 because there's no results as extreme or more extreme than our result. So there's important things you should know here. Like this is your observed discrepancy right here. Then the p-value is the amount of discrepancies that are as extreme or more extreme than yours occurring by random chance, and there are none. So the p-values are all 0. So it's very important we know what this is showing us. Amazing work right there, understanding this output. And so if we look at the conclusions right here, let's take a look at what possible conclusions we can have. So why would we not use Spearman or Pearson right here? Why are these wrong answers? Spearman and Pearson are only used, this is a great question review after the previous one. Spearman and Pearson are only used between what? So this is where you might use Spearman or Pearson. But down here, we're comparing males and females and the number of minutes they have on their phone, why are these just not right answers? Why are these just like, yeah, these don't really apply to this question? Why would those not apply? Because Spearman and Pearson should only be used when we have two whats. They're used for quantitative Shiv. Great answer right there. Used for quantitative relationships. So we have cat quant, we're not doing quant. So two quantitative variables could be described with a Spearman or Pearson relationship. But when there's a categorical X, which we have here with males and females, then we're either going to compare the means or medians. So when would you use means? When the data looks more what? When would you use means? When the data looks more what? Here's our marked up output. When would you use means? When would you compare the means for this? When would you use the means? When it looks more normal. So does this look normal or does it not look normal? We need to go to the QQ plot. Does this look normal or not look normal? So if it looks more normal and follows the QQ plot of normality, we would use means, but it doesn't follow that. So we're going to go over here and you compare medians. So the reason we're comparing medians is because the QQ plot for normality doesn't follow, and thus the proper analysis would be to look at the discrepancy between the medians. These really don't matter. The only thing to look at right here is the QQ plot to know that it's not normal, and that should immediately catch our eyes. I think there was another question people said we should do. We'll do the last one here. Question number 8. Let's talk about question number 8. Use the following output to determine the typical miss the model makes. So once again, this is a know your output type question. I love these types of questions. And here we'll zoom in here on it. Today I'm not disappearing because I need to. I'm just kind of not blocking the screen. So what was our Y variable right here? What was our Y variable right here? You can give me just the numbers of it. It's important we start at the very top of this and we know what all of this means. So what is our Y variable of interest? You can just give me the start of it. We are trying to predict what? Minutes per talk on Facebook. Great job, Kevin, right there. We're trying to predict X16. And we're using number of housemates people have. The data comes from survey 11, not survey 10 for once. The residuals right here can actually tell us, ooh, what do you notice right here? Ooh, that's a what? Actually, that's a very complex question if we go to like this, because the residuals have a major issue. This right here, wowza. Someone was missed in their prediction of how many minutes they talk on the phone. I think it's a day by 328 minutes. And that is definitely a what for the model. Like if you look at the lowest or the most negative residual is like, that's the one that's most below the line would be like this. And the one that's most above is like hugely above, like the difference. This one's this below. And that means there's a major outlier. Like that's what that would indicate right there. There has to be, because you would expect symmetry among these. Does that make sense? Like we talked about how a good correlation should look. If there's symmetry, your min and max residuals should be of decent like distance from each other. So that's a really tough theory question right there. But you would want these things to be generally symmetric. Also, we would want the median residuals to be closer to what? There might actually be problems here with the linearity, because the median residual should be close to the mean residual, and that should probably be closer to what? Like that's also a bit of an issue, yeah. So there's a lot of theory to talk about right here on this, but we would hope the residuals would be centered at 0, which means the line is going through the middle of the data. So great job, Megan. Excellent work right there. So residuals, might need to look at those residual plots, right? I'm actually run that here after this. Might have some issues with the conditions from what I'm seeing. But we have here the intercept, which is the value for people who have what? This was me when I was in Knoxville for the last 7 years after Merch left. Or 8 years. I was in Knoxville for 10 years living in the fort. Good times. So the intercept would be the expected number of minutes people would talk on Facebook for individuals who what? So I'll interpret the intercept right here for you. Have no housemates. For individuals that have 0 housemates, we would expect them to talk on Facebook for 31.808 minutes per day. Or talk on the phone. For individuals who have no housemates, we'd expect them to talk on the phone for 31.808 minutes per day. This is the uncertainty in this coefficient. Take a moment right here. Ooh, I love these types of questions. Calculate a 95% confidence interval for the estimate of the intercept. Calculate a 95% confidence interval for the estimate of the intercept. You can do it pretty quickly. I'll just take a rounded version of it. Calculate a 95% confidence interval for the estimate of the intercept. I'll show you how to do it. We should know what all this output means. This is a big review right now today. Good review to start class. So calculate a 95% confidence interval for the estimate of the intercept. Max, you're crushing it, man. Max getting 100 points. Max, you want to explain what you did right here as Brian shows it? Close, Veda. Close, Veda. Veda, you need to go a little bit more. So Max went, here. We'll go survey 11. We'll actually do it. And then we can show that we can do an estimate of it. Let me attach it so I can write the variables quicker. Max, explain what you did. Max, great job right there. And so what are people doing? This is where people are like, what? How would you possibly know that? Remember that, is it X13? We're predicting minutes per day on Facebook. There we go. Minutes per day on phone. By housemates. Data equals survey. There's our model. And then we go here to the summary. And there's the summary of the model. And we're just taking the estimate. And we're going up 2 uncertainties. Now this is an estimate of it. And this is an estimate of the lower. Confident will get us the exact. And there's the values right there. Very close. Very close. So if you do it right here. I did 2 SEs, exactly, because that's a 68.95. If you wanted to do a 95, and great answers right there, I think Veda calculated the 95, which would be level equals 0.682. Because if you do 1 standard deviation, I think that's about right. So 68% confidence interval, or 68.68 basically. But that's a 1 standard deviation. Oh, wait. That is correct, right? There's the... Something seems a little bit weird. Is it level? Is it confidence? Didn't I forget this last week? There. Is it levels? No, it's level. That is... Oh, I'm just rerunning the same code over and over again. I was looking for it to change. There we go. This is 1 standard deviation above and below, and this is 2 standard deviations above and below. How in the world do we get this t-value right here? Who can show the mathematics? This is practice. Should know all these things. How do we get that t-value? How do we get that t-value? Show me the mathematics to get the t-value. We're finishing off this output right here to make sure we know all this output. So how do we get that t-value right there? What is the mathematics? Think what is 30 divided by 2? How do we get that t-value right there? Practice, practice, practice. The t-value is a standardized metric to look at the estimate to tell us how many standard deviations it is, standard errors, excuse me, away it is from 0. So how do we get this t-value right here? How would we obtain the t-value right here? How is that mathematically obtained? Uphill practice right here. Get some practice in. Estimate divided by the standard error. Boom. Estimate divided by the standard error. So this makes a standardized version of it. And that's the value right there obtained. Great job. 100 points. People get it. And so the p-value is now telling us the intercept is statistically significant. So we think the intercept is not 0. Cool. Don't care about that. We do think it's possible that the slope could be 0. So the same thing. This would be here. 2 individuals who differ in their housemates by 1 are expected to differ in their minutes of the day on the phone by 0.039, where the person who has more housemates is expected to be on the phone longer. My uncertainty in the estimate of this coefficient is 0.43303. The standardized metric by which I can look at it is 0.091, which is close to 0, making it very not statistically significant. And also, if I look at the interval for the estimate of the true coefficient for this, what do you notice is in that interval, which coincides with it not being statistically significant? What is in this interval right here, which coincides with it not being statistically significant? What coincides with it not being statistically significant? In this interval right here, 0, because we're saying the slope of the line might be 0, which is the naive model. Good knowledge to know right there. The residual standard error is the RMSE, which is the typical miss the model makes. The typical miss the model makes. Is the RMSE, the root mean squared error, also known as the residual standard error, the uncertainty in the residuals. Do not worry that it's over a certain amount of degrees of freedom. This is just right here, calculations. The multiple R squared is basically 0. If you're wondering what that is 0.000001327. So that's that. If we times it by 100, that means 0.001327% of the minutes per day on Facebook is explained by people's housemates. Basically nothing. And what do you notice here about r squared adjusted, which is some things I want to mention today? R squared adjusted is the penalized version of r squared. Penalized r squared can be negative, always less than r squared. So it's a penalized version of r squared, penalized for how many variables are in the model. And there's one instance where it's not less. When r is 1, it's not less. But in almost always instance, let me put a star. If r squared is 1, then it's 1. But in all instances, except for r squared of 1, r squared adjusted will be less. So why do we have an r squared adjusted? Why do we have an r squared adjusted? Who can explain why we have an r squared adjusted? The reason we have an r squared adjusted is why. Because r squared will do what if we keep adding in stuff? So this is the reason why. So think through, why do we have an r squared adjusted? What's the point? We have r squared. Why do we need an r squared adjusted? Why not just use r squared? What will r squared do? Adding more variables increases r squared. So if you just add stuff in, r squared always goes up. But r squared adjusted, exactly, Megan, right there, to account for the fact that r squared will always go up no matter what. Great answers are right here. If you add in variables, r squared always goes up, because that's what r squared does. And then it's like Whitson, great answer right there. Another points to Whitson, everyone, saying like a weight. Like this is being like, okay, since we know it always goes up by adding in variables, now let's penalize ourselves if these variables aren't good, which you learn about this very quickly, that this variable is not good. You also see it down here with the p-value of the model, which is the p-value of the 1x. And so here we are right here. The answer for what is the typical miss the model makes is the RMSE. So an important thing to know right here, if you're saying what is the typical miss the model makes, that is just another name for the root mean squared error, also known as the residual standard error. And we should get, you know what, let's do a check regression, because we haven't done that. And so we should get 3 out of 10. 30 points. Woo! 30 points. Great job, 30. So we got 3 out of 10 because we did 3 questions. I didn't make a 30 right there. We got 3 out of 10 because we did 3 questions. So let's look at one last thing right here, and then we'll hop more into lecture. Might do a little bit of cleanup from last week. So too large. Need to fix the margin here. Show us how much variation is actually covered by the variables and not just the amount of. Yes, a more fair way to look at it, but it doesn't have a direct interpretation. It's a more fair way to look at it, being like after we penalize ourselves, but it's not like an actual mathematical percent of variation, but it's a more fair way, and it can be negative. It can be negative. Probably right, Whitson. Right, Whitson. How many? I'm actually shocked by this. How many of the conditions do I fail? Well, it's obvious. If you look behind my head right here on one of them. How many of the conditions do I fail? How many conditions do I fail on this? How many conditions are there? There's 3 conditions. Linearity of the x variable, and that's the linearity of the model in the simple regression, equals spread of the model. And we fail one condition right here. We fail the normality. And if I've ever seen a normality fail, and why can we check this? Why can I actually look at this plot? Step 1, look at your p-values. We've done this a lot. Step 1, look at the p-values. We see we fail 1. That's bad. Low p-value right here means a failure of the condition. All of these work the same way. Thank you for everyone. A few people have asked that. Each one of these has the same idea that if the p-value is low, you fail. So this is good. It's the same in the simple world for the model and the x, because the x is the model. So both of these are excellent. They're actually amazing. And this is also great. I mean, this was absolutely astounding because it's close to 1. This is great. It's very high. And then this right here is horrific. Everyone should be praised. Exactly. And so what would you do next after you see that you fail a condition? So this is good practice right here. What are you going to do next that you fail a condition? You just failed a condition. What are you going to do? You just failed a condition. What are you going to do? So the null hypothesis, so to talk a little bit about theory about it, if you go to classic null hypothesis, the null is that the condition is good. Like, it's a very simple way of talking about it, to say we assume that the condition is good, and the alternative would be that the condition is bad, like we fail it. So issue with condition, or condition bad, or let's go not good. We are good on the condition, or the condition is not good. Like, good complement stuff right there. Does that make sense, Megan? So the null hypothesis being everything's good, there's not an issue. The alternative being we have an issue. And so that's the way these tests are run. Like there's more theory to it than like, like if you look at how mathematically we calculate it, like the probability of a linear relationship existing given the data we see is to be a more exact way. But if you're explaining it to your boss, we might just say, we assumed to start that the linearity was what? Like the assumption we had about linearity of this model was that it was what? And just go up here to this kind of basic way of talking about it. We started out with assuming that the linearity was what? Like when I did this test, I assumed to start that the linearity was what for it? What did I assume about linearity? Yes, exactly. Here, and I'll show that here in a second too, Megan. You are correct. And so we started, and also I'll contrast these because that's where it gets confusing. So for this test, we assumed that the linearity was what? You assume is linear. Exactly. I assume it's got a linear relationship. And then I would do what right here? Would I reject the null or not reject the null? I assume it has a linear relationship. I'm saying, I think currently it has a linear relationship. And this p-value to me would indicate I should do what right now? Remember, low p-value, reject the null. High p-value, fail to reject the null. Don't accept it. You're not saying, I know it's this. You're saying, I don't have evidence to go against this. We're very careful in how we talk in statistics. We don't say we know something is true. We just say we didn't find evidence against it. So we would say right here, I do not reject the null. I did not have evidence of nonlinearity. I failed to find evidence of nonlinearity. There was not evidence. But down here, we assumed it was normal. So we're going to assume it's normal, which we're assuming that this follows over here a normal pattern. But obviously, we reject the null hypothesis and have evidence that normality is not good. We can, because the sample size is large enough, look at the diagnostic plots and we see ridiculous issues. The normality of the residuals fails. We have evidence it is not good because we reject the null hypothesis it's good. And we have strong evidence of a problem with the normality of the residuals right here. So that means our model is not a reasonable reflection of reality, and we might toss out this model, aside from it being just a really bad model. All models are wrong. This model is not useful at all. So to contrast this with the previous p-values we saw, in this model right here, what does this p-value mean? So this p-value is not a test of an assumption. This would be our model does not reduce the sums of squared error. Our model does reduce the sums of squared error. So you could say the reduction sums of squared error is equal to 0, or the sums of squared reduction is not equal to 0. But the assumption for this is that our model does not reduce the sums of squared error. So can you explain to me what it means that we don't reject the null right here? Which is, you could also say the slope is equal to 0. There's lots of ways. This one's more about the reduction because this is the full model. And this one right here would be the slope is equal to 0. The coefficient is equal to 0, which is the slope of the model. So you always want to think, what am I assuming to start out right here? And for this, we'd assume that the model does not reduce the sums of squared error because it's related to the ANOVA right here. So we'd assume that the model does not reduce the sums of squared error. And then what would we do with our null and alternative for this test right here? So what would we do right here? Because this is the overall test of the model to see if it does a reduction in sums of squared error. So now we would do what? What would we do right here? Who knows? Throw some points out. Oh, blocking it. Can't do that. So this is not a, no one's answered yet, but this is not a conditions test. This is not a conditions test. This is testing to see if the model reduces the sums of squares in a significant way to see if it brings with it information. And we would learn what right here? What would we learn from this p-value? What would we learn? 100 points on the line right here. What do we learn from this p-value? What does it indicate to us? Is this good or bad? So is this p-value right here a very good or very bad thing? Don't worry if you're wrong. Don't worry if you're wrong. If you see this p-value, you're like, ooh, that's good. Or you're like, oh, that's bad. What do you think when you see that p-value? That's good or bad? That's bad, Alyssa, right there. That's bad. This is a very bad p-value because it means that we do not reject the null and we believe that our model does not reduce the sums of squares in a significant way, which sums of squares is the error. Like you're basically saying, another way to think about this is r squared equals 0, because that means we are not explaining anything. And the alternative would be r squared not equal to 0. That's kind of a more, maybe a mathematical way. Horrendous. Yeah, this is very bad. Like there would be, in this instance, good reason to believe that our r squared is equal to 0. And if you look, kind of coincides with it. If you change up the model right here to something more classic, that we can actually do. If you do something like, you know, height and weight, you'd have a ton of evidence that height is explained by weight. So if you look at this right here, what do I do? Height and height? Yeah, I can't do that. Now we'd have a ton of evidence that height is explained by weight. So now this p-value down here, which is small, is very good. We could go through in here, look at the regression, and see that all of these actually fail, but this model's way better. The normality's got a big problem down here on the low side. Little curvature at the end of this model. I don't see the equal spread. My main problems right here are going to be problems with the curvature of the x variable and problems with the normality on the low side. This model does have problems, but it's able to explain 34.53% of the variation. It might have some utility. Does that make sense? This was a much quicker version of this right here, but this model is statistically significant. It definitely has some issues, but the model might have some sorts of utility right here. Any questions? We're going to go and finish up some notes right here. I'm going to go do a little bit of the notes from last week and take some questions to kind of review multiple regression, which is on the test. How are we doing, everybody? Let's head back to the main screen. Let me know. How are we doing, everybody? Let me know in the chat right now how you are doing and what you're thinking. That's kind of a good review. Do people feel like these topics are making more sense? We have to repeat them. We have to practice them. These are not things you learn the first time or you're like, oh, p-value is the probability of our results or results more extreme having a random chance variation given that the null is true. Brian said that. I put it in my head and it makes perfect sense. It takes multiple attempts on these. Takes a lot of practice. Thank you, Liz, right there. A-okay, I love it right there. You have to practice it. One person told me one day I woke up and it all clicked. No, it meant a lot. That was Adam, former student. He said one day it's just like what you were saying just made sense, Brian. So well, that's how it happens. Sometimes it just makes sense and other times it doesn't, but it's through repeatedly hearing it. Could you repeat the thing you said to the p-value is the probability of our results or results more extreme. I'll do one better. You ready? Give me a second. I'll show you right here. Loading something up as we end background right here. Okay. I will explain and I will show. Okay. So what did Brian just say? He said the following. Let's go look at the main screen. A p-value is the probability of our results or results more extreme happening by random chance variation given the null is true. So this is a classic definition of a p-value right here. And let's draw something out. When we're doing these tests, we're actually using a t-distribution a lot of times, and we get the following. So if we get a value of a slope and we get a t-statistic of something like 2.5, what would be as extreme as 2.5? So that's our result. What would be as extreme as 2.5? Like a slope of 2.5 standardized to a t-statistic would be as extreme as what? So what if we talk about our result was a t-statistic of 2.5? So that's our result is a t-statistic, which is the standardized way we can look at the slope. Our result was a t-statistic of 2.5, then as extreme, great job, Max, right there, would be negative 2.5. So when we talk about just as extreme as that, so results more extreme, or as extreme. Results more extreme. So that's as extreme or more extreme right there. Because we're looking at slopes that could be negative or positive in this instance. And now we want to find the probability of things more extreme than it. So results as extreme or more extreme. Results as extreme of our results or results as extreme or more extreme. As extreme. So there's as extreme. Or more extreme. So more extreme is going to be, there we go. So what's the random chance variation? The random chance variation would be the what? If I talk about random chance variation right here, The random chance variation on this is the what right now? Like, what is the random chance variation? It's the what curve. The random chance variation is the normal curve right here, or the permutations we get. When you look at a permutation procedure, which we saw in some of the questions, the permutation procedure, if we do a permutation procedure like, let's do here associate. If we do associate XO2 tilde XO3, we want to reverse these. Here we'll go XO4. If we do this right here, we will get a permutation procedure. And the permutation procedure is showing us these distributions down here. And you can tell the p-values on these are both what. The p-value for both of these examples right here are what, because you can actually see there's no area on the side. So it's saying to you that the probability of getting something as extreme or more extreme than our results would be 0. I'll have to go back to that and take a look. I'll take a look. So right here, you can see this is the p-value, is the probability of our result or results as extreme or more extreme happening by random chance variation, given that the null is true. Why is the PO really low on the linearity test with the diagnostic plots bad? Good question. I think this is the one we just did right here. The p-value on the linearity test is bad. This one's not the easiest one to see. Are you talking about, so Cole, we'd look for the linearity right here, and there's a bit of a bend here at the end. If you look at the way this looks as a linear relationship, we need to visualize the model. The line does not completely go through the data. Please know, which plot do we look at for linearity? 1, 2, or 3? Which plot do we look at for linearity? 1, 2, or 3? Which plot do we look at for linearity right here? 1, 2, or 3? We look at which one? 1, 2, or 3? Which one is the linearity? Which one would we look at to say, let's examine the linearity of the model? 1, 2, or 3? I'm going to wait for a lot more answers. The answer is... which one? 1, 2, or 3? The answer is plot 1. Not trying to trick people, just want to see if you know it. I guess I was trying to trick people a little bit. The answer is plot 1. This is the line of your model right here. The answer is 1. What is the only thing you look at for plot 3? What is the only thing you look at for plot 3? Plot 3 only does this. There's a residual plot right here. There's a residual plot. There's a histogram of your residuals. This is a QQ plot for normality of the residuals. So what's number 3 for? Just for normality. Number 3 is only for normality. What is plot 1 and 2 used for? Plot 1 and 2 is used for what and what? Plot 1 will have us examining these two issues right here, the linearity, which is the line, and the equal spread, which is do they equally go around the line? So those right there, equal spread and linear, exactly. And then normality of residuals, only look at this. What's the histogram good for? It's the Lane Kiffin of this output. Sorry, Lane Kiffin. What's the histogram good for? You tell me. It's the Lane Kiffin. It's good for nothing. Get that right there. Take that right there. Memes. We still show respect to it. Still show respect. We can say it's good for nothing. We don't throw stuff on the field at it. Just putting that out there. Good for nothing, though. Just still be respect, though. You can say that. Good. Make jokes. Make memes. Don't throw mustard. Okay, so that's what we got going on right there. Let's take a look at some notes right here. Hopping back a little bit of a notes view to our end class. Let's go back to notes review. Here we go. Doing it. Don't do that, Megan. Only if it's okay with that. Only if it's okay with that. Hopping into some notes right here, doing some review. Let's go and go reverse order. I'm going to go reverse order to finish up. I want to make sure we covered everything, and let's go and do some reverse order right here. So, okay, let's go right here. One of my favorite examples. Here we go. Is there a histogram meme already in the Discord right now? Is there really? Okay. Okay, I got my side. Is it in the general? Oh god, who made this? I'm giving 100 points to this right here. Oh my god. I gotta share this with Dr. Petrie. Who made that? I gotta see who made it again. Max, man, Max. That is awesome right there. Oh gosh, you're making my day, Max. This one is definitely normal. Okay, I'm sending this to Petrie right here before I even 2 seconds. DS320 meme made from students. Okay. Sending it to Petrie. Okay. Attachments are still loading. You can send. That's sent to Petrie right there. Man, that's some good stuff. That's some good stuff. I love it. Good usage of Anakin Skywalker there, right there. Okay. Darth Vader, don't follow Darth Vader. Don't do it. Don't be like Darth. So here we go. When you look at this model now, we've jumped into the world of what kind of regression. We got 20 minutes here. We'll finish off these topics. When you look at this model right here, you've jumped into the world of what? This is review. You've jumped into the world of what by doing this? The y tilde dot is going to change our world forever because that's all the x's. That's all the x's. So you're jumping into the world of multiple regression. Kevin knows what's up right there. Vader knows what's up. So we got the world of multiple regression. So now, for something to be statistically significant in the multiple regression world, it means that it does what? Which, if you think about abdomen, that's probably one of the best things to tell if you've got body fat. I mean, like, everyone puts on fat differently. I think I put it on my face. But, like, abdomen is kind of... It's kind of a general thing. Megan, you're on the right track. Go a little more detail on it. What does it mean for multiple regression for something to be significant in the multiple world? Pretty much, Kevin, right there. With the other variables in the model, abdomen explains a significant portion of the variation not accounted for by the other variables. So you might say, well, wait a minute. Somebody's weight doesn't explain their body fat. Somebody's weight is not significant in explaining Kevin's points right there. Why do you think weight is not significant in explaining body fat? Why do you think weight is not significant here in explaining body fat? Which is weird too, because weight has a negative coefficient with body fat, meaning two people who are otherwise identical but differ in their weight by 1 pound, the person who weighs more is expected to have a lower body fat by 0.08. Pretty much right there. And you have to hold all else equal because we're saying with the other variables in the model. So what it is that weight is probably highly correlated with other variables, not just height, but all the other variables in the model. It probably shares the variation. So weight is not bringing with it enough what? Weight is not bringing with it enough what? Weight is not significant here. So it's not bringing with it enough what to be significant in this model. You are correct, Justin. Additional, yeah, I'll take additional right there. New info, new information. So it has to do things that the other variables are not accounting for. How can you take a look at the overlap between these variables? How could you see kind of where the variables are overlapping and what they're doing where they're stepping on each other's toes? And there's a lot of ways to talk about this conceptually. How could you see where the X's are stepping on the X's toes? Great answers, everybody, right there. Good practice. How could you examine mathematically these things? So how are we going to mathematically calculate a way of saying, well, what are the X's doing that's interfering with each other, that they're bringing the same stuff to the party? How can we do those calculations mathematically? Because that's what we'll review next. Because now we're going to be like, well, these variables are probably like fighting each other and being like, no, I want to explain this way. I want to do this. Because they're all here trying to explain variance inflation factor. Great job, Nathan, right there. Variance inflation factor. VIF stands for variance inflation factor, and that'll be calculated from the R squared sub I. So this confidence intervals, making estimates for coefficients. We did stuff. The uncertainty. Here we go with variance inflation. So variance inflation is calculated by the R squared sub I. And the R squared sub I is for the what in the model. When we say sub I, that's for the what in the model. Why is it R squared sub I? Because this would be technically, well, that I right here. What should that I be right now for this model? If you went through and calculated each one, right now we're calculating R squared sub what? Because it's R squared sub I, because it's for each X in the model. So right now we'd be mathematically calculating R squared sub, and there you go, Megan, great job right there. It'd be R squared sub 1, because we're calculating for the first X in the model. So this is a good or bad thing to be high. Like if I told you this right here was something like 98%, is this a good or bad thing? Is this a good or bad thing? Is this a very good or very bad thing? Like, ooh, 98% r squared, but this is r squared sub I, which says that the first x in the model has 98% of its variation explained by the other x's, because this is a model made from the other x's. This is a very, very bad thing, because it means that our x's have redundant information in them. That 98% of the variation in the x, which is the information in it, is explained by the other x's in the model, so there's redundant information. Which if there's redundant information, this will increase the standard error. Now, how can we figure this out? Who right now, for 500 points, can figure out the VIF right now of this hypothetical first x? I think this is a pretty easy problem to solve if you know how to solve for VIF. You can put this on your cheat sheet, but what would the VIF be of this problem right here? What would the VIF be? What would the VIF be of this first x right here if it's r squared sub I, which for it is 98%. Close. You thought I was doing that right. Close. Close. Did I say 500 points? I'll throw it on. Max has got it right there. Whoops, 50. Yeah. Close. 1 over 1 minus r squared sub I. Great work right there. Good practice. So we're just plugging in the r squared sub I. And now you need to know, well, 1. So this right here is 50. And pretty easy, our uncertainty is about how much higher in this estimate. So when we estimate the coefficient for the x, we have about how much more uncertainty. Remember, this is variance inflation. So if you want to get standard error inflation, you can do this. Just round it for me. It's very close to a nice number. So about how much, and so you need to do all this. If you want to get standard error inflation, you got to do that. So about how much more uncertainty? Exactly, square root of 50, which is very close to what? Which is not good, saying we have about this much more uncertainty. We have about a factor. It would increase our confidence intervals. So 7, exactly. It's almost 49, so it's about 7 times the uncertainty. And when we think about this, so a lot of the formulas are shown here next. We do not want our x's correlated. Know those boxes. Here's the variance inflation formula. If I told you the model only had a r squared of the model equal to 80%, which is very close to your homework assignment, what would be your cutoff for a high VIF? So what would be your cutoff for a high VIF? It's basically on the bottom of the screen. So what would be your cutoff for a high VIF? If you take this from the model summary and say, because now you can use it as a model dependent, it'd be 5. And so it's 5 because you're just plugging that in to use it as a model dependent. And this is, we're just using it for the model, which is the next slide, I believe, using it as a model dependent. So this explains if you make a model dependent high VIF cutoff, you'll just run the same formula again, where this is your r squared from your model to make a model dependent high r squared. Multicollinearity does not invalidate your model. It just increases your amount of what in your estimates. Multicollinearity does not invalidate your model. It just increases your amount of what. Answer is standard error, but I don't like hearing standard error. It's just going to increase your amount of what in your estimates. The answer is standard error. It's going to inflate standard error, but standard error is just a term for what? Uncertainty, Walton. Yep. And we don't like that. It just means you're more like, I don't know. We don't like that. We don't want to be like, I don't know. So the standard error is your uncertainty. It's going to really hurt you because you have redundant information. Your model just doesn't know what to do. So it inflates the standard error, increases your uncertainties. You don't like this, and you can get an estimate of about how much those uncertainties have been increased due to the redundancy. Statistical significance right here is the total reduction in the sums of squared error from the what model. This is a review once again. Once again, reviewing. Please slow me down if you have questions. But statistical significance is the total reduction in the sums of squares from the what model. Statistical significance is the total reduction in the sums of squares from the what model. We always start with this model, unless we're doing a partial. Here's your starting point. Here's your model. And we're looking at the reduction going from here to here. And we're trying to look at the reduction, which that's a pretty good reduction. That's how much r squared we have. The naive model is the starting point. So the naive model is the mean of y. So the mean of y over here is the starting point. And there's no x's in the naive model. So the naive model is the starting point where we don't have any information. No x's yet. Here's a model with multiple x's in it. And we can see the overall reduction is going to tell us whether the set of predictors brings with it enough information. If the p-value is less than 0.05, it brings significance. If it's higher than 0.05, they're not significant together. So check this out. This variable right here is or is not statistically significant. There's a review again now. Number of total offensive plays that a team has is or is not significant in explaining if they win games. Is or is not significant. Pretty simple right there. That is or is not significant. It is, because the p-value, because it's significant. It's highly significant. It's very significant. But how about offensive total plays right here? And if you're wondering, that as a decimal is the following. Is this statistically significant in the multiple world? Is it now statistically significant here in the multiple world? Is offensive total plays significant? No. Because if you think about offensive total plays, it's from people's rushing yards and passing yards. So the information about if a team wins is probably contained in these variables and then is probably redundant with how many plays they have. So predicting a team winning, we don't need this extra variable right here. It's bringing with it information already contained in these other variables. So it was significant in the simple world by itself, and in the multiple world, it's not significant because it's probably we know it had information, so the only way it would not be significant is if it doesn't bring enough new information. It had good stuff. It was very significant, but then in the multiple world right here, the other variables are already accounting for the variation that it's explaining, so it's no longer statistically significant because it's not bringing with it enough new information. Does that mean that total plays does not explain if teams win? No. Total plays explains that teams win, but in a model with extra variables, it doesn't bring with it enough new information that the other variables are not accounting for. So in this model, it doesn't do anything important. We could probably remove it. All that good stuff right there. You'll notice right here a very complex model, and the only way things are significant right here is if they bring with it new information. But this gets us, if you just throw out all the variables that not bring new information. Well, no. Good, Max, good question right there. Let's go to Max's question. Max says, let's start throwing out these variables. If I start throwing out these variables, what would happen to r squared, Max? Max, amazing theoretical question, which we should know the answer to. If I start throwing out, and Kevin knows a good answer too, which we're going to do next, and so this will be good review. If we start throwing out x's, then what will happen to r squared? If you start throwing out x's, what will happen to r squared? R squared goes down. Now, r squared adjusted might go up. R squared adjusted could go up. But you can remove out one variable out of the model, but you cannot remove out multiple non-significant. And huge thank you to Kevin right there, who literally got to the next slide. And Kevin, great job. You might have read through, but you cannot drop out multiple significant things because it's like a Jenga. How many pieces, think of this as Jenga. How many pieces are you allowed to remove in Jenga at one time? I'm sure a lot of people play Jenga right here. If you've never played Jenga, amazing game. How many pieces are you allowed to remove in Jenga? We're just viewing it from this side right here. How many pieces do you get to remove from that Jenga tower at one time? When you remove something from Jenga, and this is your model right now, your model's a Jenga, so you're going to remove one piece at a time. Because everything starts to shift around a little bit when you move things out, and then you have to reevaluate. You move out, you take out a piece, and then you look and you say, how are things looking? But you got to be careful because it's going to shift everything. So when we do this, if we remove out one thing, we're allowed to do that. But we can't start removing one thing. I know that sounds crazy, so maybe my Jenga analogies, first semester I made it, might work on a little bit before I redo it again. You have two choices right here. Choice one is to remove out one thing and stop. Don't remove out others. Choice two is a bunch. What you can't do, because you're saying, aren't these the same thing? You can't remove out one, remove out one, remove out one, remove out one. You need to either remove out a bunch at once or one at once. And let's look at this. What this is called is a partial f-test. Now, the way a partial f-test works is we remove out a bunch of variables at once and we look at their impact. So let's view this visually right here. I'm going to draw a drawing. What does the f-test compare again? The f-test compares the what model to the what model. What does the f-test compare? If we do a full f-test, the f-test would start with the what model, because the f-test is the total reduction in sums of squared error, the total percent of variation explained. It's going to go up to the complex model, which has everything in it. That's just all x's. So this is all x's. That's every one of our x's. All the x's. But the F test will start with the what? If you do it just the F test, just in ANOVA. Oh, we'd have to go back. That is the standardized metric by which we can look at an estimate. So what is the F test going to look at? That's the standardized metric right there, Nathan. What is it going to start with down here at the very bottom? What will it start with? What is our jumping off point to start by seeing what the error is? Not quite this simple yet. Not quite. The F test is going to start, and this is just the F test, like the full F test. The full F test would start at the very beginning with nothing in it. The full F test is going to start with the what model? Nothing in it model, no x's model. So we want a model with no x's. What model has no x's in it? A model with no x's, where you have 0 x's. Maybe up here we have like 5 x's. A model with no x's, like no x variables, would be the naive. And if you do this, you have just done an F test. But what if you don't want to do that? What if you want to go from a 2-variable model up to your 5-variable model? You're now doing a what? If you want to go from a 2-variable model to a 5-variable model, you're doing a partial F test. And the model down here is called a simple model. Might as well be called a simpler model. So the partial F test compares part of the way. It compares part of the reduction in the sums of squared error. So here we can see what a partial F test does, where it doesn't compare the naive to a complex model. It compares a simple model to a complex model. So a simple model is just a model that has what to a complex model. Because we could do the partial F this way. Here's another partial F. So that's a partial F right there. We could do a partial F this way. That's a partial F right there. It's just going part of the way. So a partial F test will always be where we compare a simple model, which has what x's in it. It's not doing the full F test, which is the naive to the complex. It's doing a test of the simple model, which has less x's in it than the complex test. Does that make sense? The complex model, not test, but complex model has all your x's in it. But a simpler model, simple model, has less x's in it. And then we're asking, is there a what in the sums of squared error between these models? What are we asking? We want to see if going from the simple to the complex, we observe a what in the sums of squared error. What is our goal always with the sums of squared error, which is how much our model misses by? We're always trying to what that sums of squared error. We're always trying to do what to that sums of squared error? Exactly. We're always trying to reduce that sums of squared error. So we're always trying to reduce it. If we get a p-value less than 0.05, we have a significant reduction. If the p-value is greater than, there's not a significant reduction. So if you take a look at this test right here, we're making a simple model right here with the following variables, and we have a complex model with all the variables. Running the ANOVA right here is how to run the partial F test. This is the partial F test. When you look at the partial F test right here, you can see the differences in the coefficients in the model. This was removing out all the not statistically significant models. This is statistically significant, which means that the variables we removed out, the 5 variables, reduced the sums of squares in a significant way. So we cannot eliminate that subset of predictors. Those predictors that we removed actually reduce the sums of squares in a significant way that is unlikely due to random chance. So when the p-value is low on the partial F test, we'd go with the complex model. Let me put that in the chat right here. When p-value is low on partial F, evidence to go with complex model. Probably the best way to summarize it right there, low p-value, we should go with the complex model. Practical significance, we've been talking about R squared, and it's the percent of variation explained. I do want to just mention R squared adjusted again. The things you should know about R squared adjusted with our last few moments right here is R squared adjusted is simply R squared with a what on it. R squared adjusted is simply R squared with a what on it. First thing you should know. It's R squared with a what? It's R squared with a what? Penalty. So that means it's going to be less than r squared, unless the rare instance when r squared is equal to 1. Then the penalty term goes away. Don't worry about that. I don't never like that trick question. But r squared adjusted can also be what? Second thing you should know is r squared adjusted can also be what? Last minute of class. R squared adjusted can also be what? You see it right here, which is something r squared cannot be. R squared adjusted can be this. Because if r squared was 0, then r squared has to be lower. The ones that exactly. Yep, you're using it to compare models, Max. Great question right there, Max. The ones you think about throwing out, you could put in the simple model. So you're like, we should maybe take these variables out. That's why you use a partial F to say, should we use this model or this model to compare two models? And so r squared has no interpretation. Really good, nice stuff right here. And you want your r squared and r squared adjusted to have close values. So all of these notes right here, and I think that does it, except for the RMSE, which we talked about. And then we've done predictions and stuff. The RMSE is just the typical miss the model makes. And that's been a good review today of some complex topics. That's literally got it right here. Hang out for a moment if you got questions. Let me know. Class bell's going to ring, right? 3, 2, 1. Where's my bell? There we go. Class is over. If you have questions, let me know. Thank you, everybody. Did a lot of review to start. Today was like a huge review day. How do people feel? I'm hoping today feels like a big review day. We literally went through, we did correlation today. We did simple regression today. We did multiple regression today. A lot of different things. Let me know if you have questions right now, but we did a lot of questions. Let's throw out some 50 points in class. Good review. Kevin, thank you so much. A lot of review. Yeah, today was a very dense class. Contrast that to last week when we had to take some breaks. So you got to take breaks if you got to. I mean, it's by definition, right? But all these good things right here, we are caught up in the notes to where we need to be. But knowing, so to go to Max's question, thank you, Clayton, right there. I appreciate that. So Max, does that make sense why you would use a partial F? If you have two models and you're like, well, I've got this model with these variables and I've got this model with these variables, which model should I use? So the partial F test, you'll put the complex model, comma the simple, and then you'll see if there is a significant reduction in the sums of squared error. So you're just simply asking, which model should I use? And when the partial F comes back significant, that means there is a reduction in the sums of squares. So go with the complex because the variables are bringing with them new information. So good stuff right there. It's a test to see. Awesome, Max. Let me know those other questions you got. Wait, wrong button. Well, back to the main screen. Man, happy to be back to normalish. Woo! I love it when I thought I was going to teach on Monday. Monday I was like, I'll teach class. And then I was like, no. We ended last class with cross-validation. Oh, we got through all the notes there. Awesome. We're going to go to chapter 6 today. My gosh. I'm looking up some notes here in the background. Chapter 6, Judgmental Forecast. Fun stuff. Awesome stuff. Are you teaching 14? Am I? Let's see. Do I have my phone near me? Am I? I think I am. Am I? Wait, am I? Am I teaching? It might be the one semester I'm not teaching it, but I'll be here to help, and we'll have our Stat Nation 2 Max. So join, keep on the Discord. Every semester we're going to Discord more. So it helps as people continue on the Discord, continue in the different groups, and then we continue to grow things. But just keep with the Discord because as you can tell, the more people we have utilizing it, the better it goes. If no one's using the Discord and it's just like me on there talking to like one person, I mean, that's all right. But our goal is to keep growing it. Oh, no, I'm sorry, Shiv. Thank you so much. I appreciate people like, hey, Brian, are you teaching? Like, that means a lot to me. But I'll be helping out. I'll be answering questions, doing my office hours. I can still kind of answer questions. I'm allowed to help out with classes I teach. So I guess I'm not teaching it. So I guess I'll be doing 201 through 2475. Man, I used to just, back in the day, just teach 201. I'll tell you, it's pretty, right now I'm teaching 4 different classes, technically 5, teaching 6 sections technically. So man, last week, my brain was fried. I was like, too much. But no, we got this. We start off here in a little bit. But no, thank you everyone for all the positivity. We love that positivity. We got so many cool things, so many cool topics, and all these things really converge. Just takes practice, but you got this. One big suggestion I have is do some data camp over winter break, and you'll walk into 474. 474, let me give you some big props right here. 474 starts with a review. So if you take 320, 474, like right in a row, you walk into 474 and you already know some stuff. Like you'll be good to go like first 2-3 weeks. So 474 starts with a review. We go back through, we do how to do like just general coding with vectors, with all that stuff. You actually review a lot of the 320 notes. So don't be too afraid of 474. It's actually a much easier beginning than 320 unless you don't know the stuff, because we want to make sure people have a very strong foundation. So we kind of just work on that foundation again of your house and make sure you have a strong start. So 474 lets you practice at the beginning again before we get serious. So this time we start you off with the basics again, but we try to reach you to a higher level. So the more you've been practicing, the more you've been coding, a little data camp in the background, you can walk into 474. And I've had people be like, this is easy. But if you don't practice coding, or you wait like a year and your coding skills go away and you have to refresh everything, it can be tougher. But that's why we have it, because we don't know if everyone's going to take them in sequence immediately. So we don't want to be like, oh, you took 322 years ago and you don't know anything. It's like you forgot everything. Then we don't want to totally lose you at the start. But I think that's got it. We'll be doing office hours here in a little bit. I will see everyone then. Shiv and Max and Wilton and Clayton, good to see you here. And Lindsay and Kevin and everyone and Emily, I'll see you guys then. 100 points in class. Bye for now. Papa Joe.
Yes.